Hi, this video lesson is about the Doppler effect, which is the influence that motion has over our perception of sound as an object moves. Now the Doppler effect gets used in two very prominent ways. One of them deals with sound, which we're going to study here. The other one would be the Doppler shift or the Doppler effect that is used when looking at how other galaxies and other stars are moving relative to us, looking at that blue shift and red shift. So all waves do this, right? Every single type of wave, whether it's an EM wave, whether it's a mechanical wave, doesn't matter. All waves are going to undergo some Doppler effect so long as there is motion involved, whether it's motion of the source or motion of the observer of that light or sound or the observer of the wave. So if you get movement towards something, right, there's going to be a higher frequency associated with that. Picture yourself standing still, and if a car is driving towards you honking its horn, the horn is going to sound as though it's a higher frequency or a higher pitch than when it moves past you. So if you're standing still and that car drives by and it continues to honk, that horn is going to undergo an audible shift where that frequency will now be lower than what's actually being emitted. Right? The big assumption that we make here is that the air is stationary, right? So when we talk Doppler effect of sound, we're going to assume that the air is not moving. How this then pertains to shock waves, right? Quick little aside here. When objects travel really, really fast, right? And we're talking approaching the speed of sound or beyond the speed of sound, we actually observe these shock waves and we can hear these sonic booms as objects travel by us. And this little simulation here is going to show us what happens, right? The Doppler effect and how we get the sonic booms here. So the first one that we look at is with the stationary sound source. So if you look to the left-hand side here, stationary source isn't moving. It's going to emit some frequency, and the wave pattern is going to be spherical, and it's going to be very, very easy to observe, right? Nice, uniform, nothing's too crazy going on there. Was this source begins to move. So in this one, the source is moving in this simulation at 70% of the speed of sound. Here to the right-hand side, we notice the waves are bunching up in front of the source itself, which means that's going to represent a higher frequency. Even though the object is emitting the same frequency as it was before, once you put it in motion, we observe that wavefront bunch in front of that sound producing source, which is going to cause an apparent higher frequency for an observer listening. If you notice behind the moving object, now we see the wave pattern spread out more. So again, the object is producing the same sound, the same pitch, the same frequency, but if you're behind the object, we're going to observe a lower frequency because it's moving away from us. As the sound source continues to move faster and faster and faster, this is where we're going to get that sonic boom, right? That boom boom that you would hear as a fast moving object moves past you. And depending on how fast you're moving compared to the speed of sound, if you're moving much faster than it, we actually develop this cone here, right? And that cone is going to represent that huge pressure that's building up behind the object itself. We don't necessarily get that gigantic pressure up above when we're moving at the speed of sound. But here what we observe is you're not going to hear it until it gets to you or beyond you, depending on your location. The important thing to note is this one here, right? If you are in motion, what happens as objects are in motion? Are you going to hear a higher frequency or a lower frequency based on relative motion? And what we observe here, right, with our mathematical formula is what happens when the observer is moving. Our formulas that we're going to look at are going to slightly change. If you see a subscript O, that stands for the observer. A subscript S stands for the source. Our velocity of the observer is always going to be in the numerator here. And think about the ratio that this is talking about here. If the observer is moving towards the source, that's going to cause that sound to apparently bunch together, which is going to drive the frequency that we hear up. So if the observer is moving towards the source, we're going to add. If the observer is moving away, we're going to subtract. That movement away, no matter what, is always going to try to cause that frequency that we hear to go down. If the motion is towards, that frequency that is observed is going to go up. If the source is moving, right, so if we come down here, and if the source is moving, now our velocity of our source is in the denominator, but the same concepts apply. If the net motion is moving towards the observer, that observer is going to hear a higher frequency. Well, now we would need to subtract, because if we subtract, that's going to make the denominator lower than the numerator, which is going to cause that ratio in that parentheses to be greater than 1. If that ratio is greater than 1, the observer hears a higher frequency. If the ratio is less than 1, we're going to observe a lower frequency, which is what the second bullet point is saying. If we add our source velocity to the speed of sound in air, right, if we add it, that's going to mean the denominator is greater than the numerator. The observer will hear a lower frequency. And again, net motion being away is going to cause a lower frequency to be heard. I suppose I should make one more point here. Just the plain v without the subscripts, that is the speed of sound in air. So v without the subscripts is speed of sound in air, which you can find with delta x over delta t, or by knowing an air temperature. In general, for our Doppler effect, we can look at this if both of them are moving or if just one of them is moving. And we see the exact same ideas here. So the first bullet point, use plus v sub o and minus v sub s if the motion is towards. So if you know that the observed frequency is going to be higher than what's actually being emitted by the sound producing source, you're going to add VO and you're going to subtract VS. If the motion is away, we're going to subtract VO and add VS, because again, that's going to play with that ratio in the parentheses to cause that observed frequency to be lower than the source frequency. A little word to the wise here. You do not always add subtract if the motion is towards. Think about a chase scenario. If you have two objects that are moving the same direction, the faster one is going to be what truly dictates the frequency that's observed. If you have a chasing scenario where, let's say you have, two cars and one car is gaining on the other car, well, there we could have a plus plus or a minus minus depending on how you look at this. Right? So don't get in this mindset of if you add VO, you always subtract VS. No, because you have to look at their independent motions. What is the motion of the observer doing? Is their motion going to cause their frequency that they hear to go up or go down? And then ask that same question for the source. Is what the source doing going to cause the frequency to go up or to go down? Because when you get two things moving in the same direction, one of them is trying to get closer, one of them is trying to get further away is really what's happening there. Right? So don't be afraid to play around with the pluses and the minuses. But again, make sure you look at it and recognize what's happening. If the motion is towards, the frequency has to be going up that's observed. And if the frequency is going down, that means the motion is going to be away. There's a quick look at the Doppler effect and how motion is going to impact what we hear.